Hey guys, it's Karsten with Robbie, and we're going to show you Project 2 for 357. So if you recognize the main component of our circuit, we detailed this in our last video. This is the light circuit where we're comparing the output of our two photoresistors, and we have a three-state output. So we've taken this circuit and we've interfaced it with our computer using the lab jack and the NXT. And in addition to that, we've included two solar cells here, and that allows us to monitor the power output. What we've done is we've run each of these solar cells between a 1K resistor, and we're using that in conjunction with the lab jack to get the power that are incident on these cells. So we're going to compare whether tracking the sun is going to be more efficient than just having a stationary solar cell. With the NXT, what we've done is we've used the lab jack to measure our three states, and then we've using the LabVIEW code that Robbie will show you in a minute, we're using that to drive our NXT motor and to actually physically track the sun on the solar cell. So as you can see, if light is incident more on one side of this divider that we've created, our NXT motor will move in the direction to try to equalize the light, and if it's on the other side, it can go the other way. So we've created a tracker. We've geared the motor here so that the steps are very short, allowing us to have very fine precision and control over our motor as the sun doesn't move very quickly across the sky.
Oh, it's working.
So that's about the gist of what we've done here for Project 2. For more details on the LabVIEW, Robbie will be taking us through the interfacing with the computer.
Okay, so as Karsten mentioned, we have our circuit over here that tells us which side is brighter or whether the solar cell should move or not. And those three states are piped into the lab jack, and then we also have two resistors over here on the side so that we can calculate the power coming out of the solar cells, and that voltage is ran into the lab jack as well so we can read it on the computer, and since we have a 1K ohm resistor in there, we can easily calculate the power output by each one of the two solar cells. Once you get over here to the LabVIEW code, you can see the inputs coming in from the lab jack. They're put into three Boolean indicators on the front panel, so right now we're looking at the block diagram. And we also have the voltages coming in, so you can see the movable voltage up at the top, which is displayed on the front panel. The three states are ran in, and then the stationary solar panel voltage is there on the bottom. Once you get those states into the computer, we have a case structure and a timeline, which allows the motor to move whichever direction it needs to seek the equivalent brightnesses among the two photoresistors. So if it is brighter on the left-hand side, it will move towards the left in order to make the right one brighter so that they each have equal brightnesses. Down at the bottom of this while loop, we have the code that takes the voltages from the two solar cells again, and instead of displaying them on the front panel like previously, we take them out of our while loop and we save them to a file so we can go through and analyze that data later. So, here's the code, and once you get over to the front panel, you can see the things that I was talking about. So we just have the indicators up there at the top so that we can see which side is brighter. And then we have the movable and the stationary solar cell voltages, so again we can talk about the power. And as you can see, the lights are changing because the light on the photo resistors over there is changing due to Karsten. And you can see that that will cause it to move. So for instance, you can cover up this side, so it's getting dimmer on that side, so it's trying to move it to our left in order to try and even out the resistances.
The LabVIEW code Robbie showed you outputs a text tab delineated text file upon termination, just like this one. This is a experiment we performed over the course of a day using our solar tracker and the two solar panels as was shown. And after some manipulation in MATLAB and a little graphing in Excel, we produced this plot which shows the power of the solar cell, each individual solar cell outputted against the time. And as you can see here, the motorized cell, shown in red, performed much better than the blue one. Most evident is when the sun is low in the sky during dawn and dusk. The motorized cell was oriented towards the sun and did significantly better, while the stationary cell quickly decayed away and dropped off. The power dropped off. Over the course of the day, it was also a lot much more constant, straight line, although there were plenty of natural variations. You can see something like a cloud or something here. But overall, I think it kind of shows the principle behind this. Obviously, it's not the best data set, but given the what we were working with, I think it shows that the principle at least is sound, and our circuit performed well.
So we learned a couple things when we made this circuit. First off is that LabVIEW does not support simultaneous while loops, so you can't have separated case structures. So that was interesting, but besides that, we also learned quite a bit about using LabVIEW in general in order to interface our circuit, move our NXT motor. We use the frame commands in order to decide exactly how long to move the motor, and that the structuring of those commands was something that took us a little bit to figure out, but when we got it done, it worked pretty well. So we were pretty happy about that. Probably cut that.